So 16.6, we talk about parametric surfaces and their areas. So far, we have considered special type of surface, cylinder, quadratic surface, and graph or function of two variables. Do you guys remember the cylinder and quadratic surface? So what's the quadratic surface? Those are examples. So the equation in our XYZ, and the high power on the variable will be 2. Pi has something to do with the square. So the highest power on those variable will be 2 only. The equation for those, the graph of those equation we'll call quadratic surface, okay? And we have ellipsoid and cone, etc. Okay, so those are quadratic surface, and we also have cylinder before. Okay, so that's what we learned before. And today we talk about parametric surfaces, okay, and their areas. So now here are some examples of family of parametric surfaces, okay, and let's see when would I use this, okay, when would you use it, okay? So let's take a look over here. Let's look at the first example. First of all, parametric surfaces are defined by three-dimensional vector function of two parameters. Okay, and such surface used to model the shape of many objects. For example, let's take a look at the first one. Who want to read the first one? All right, I'm gonna copy. Benji? Okay, Benji.
Primatologists use augers to examine isomorphism of an object. The shape of an auger can be modeled using the parameter.
All right. Okay, great. Okay, so that's the first one. Okay, the second one. Who want to read the second one? Okay, Isaac, go ahead.
Many biologists can study the cell at many cells, studying those of novel. Studying surface of a novel cell is modeled using parametric.
Okay, perfect. Good job. Okay, the last one over here. Who want to do that? Okay, Melanie, go ahead.
Solid scale resolution can be modeled using a specific form of parametric surface. Antique dealers can use such surfaces to compare the ideal form of a base to its current state to identify areas of wear and structural damage.
Perfect. Good job. Okay. All right. So you see some example of parametric surfaces, right? Okay. Now let's talk about what are they. Okay. So in much the same way that we describe a space curve function, at that time, how do we define the space curve? Right. See right here. At that time, we have this variable t, and then we have a vector function on this t. T is a parameter, okay, and that will define a space curve. Okay, the tip of the vector trace out a space curve. Now today, we're going to have a vector function, but this time instead of one single variable over here, we're going to have two different variables, u and v. We are going to have two parameters, okay? And see the u and v, this is the uv plane. Okay? So, and then this vector function is going to map every point in this region, okay? And to a surface, okay? And using u and v as parameter. So here is some visual picture of this, okay? So you take every point here, and then you apply this vector function on u and v, and then you get a corresponding point over here. And then every point here mapped to every point in this surface right here. Okay, so that's the map. Now, how does it work? Okay, this one here, this vector function, it has two parameters, u and v, and it's going to have three components. The output will have three components. It's going to be in the 3D, right? Okay. So the first component, the x component, what should I put over here? The y and the z. So the x coordinate of this, okay? So this, suppose this point map to this point, the x coordinate this. How do we represent this? That will be a function of this two parameter, u and v. So that will be x of u comma v. Okay, so the x coordinate is a function of the two parameter u and v. Similarly, the y coordinate over here with this point is a function of u and v. So that is y of u and v. Okay, so function u and v. And then the last one here, the z coordinate is also a function of u and v. So that is z of u and v. Okay. All right. Okay. So basically every coordinate x, y, and z, they are functions of u and v, using u and v as parameter. Okay, so like this. So this is a vector value function defined on this region, okay, on this region D, okay, in this UV plane. So the component function are function. So each component function is a function of these two variables, u and v. The domain over here will be the D over here, okay? And then the set of all those points here, such that x equal to what, y equal to what, z equal to what, will be this surface over here, this parametric surface right here, okay? X equal to what? What should I put over here, you think? The set of all points in R3 such that x equal to what? The x coordinate is x of u and v, is a function of u and v, right? Y coordinate is a function of u and v. Z coordinate is a function of u and v. And then all those points, okay, when you put them together, you're going to get the parametric surface. Okay? And here's an example. Okay, this connection. Now, this one over here is called, this three equation over here, those are called parametric equation of the surface, okay, of this S over here. Okay, so this one over here is called it's the vector function. Okay, it's a vector function, and then these three are the parametric equation of the surface. So try to think about this way. Now you take u and v here inside this D, okay, and then it's going to map to a point over here on this surface S. Okay, think about that under this function. Okay. Each one is going to map to a point on the surface. Okay, so in other words, this surface here is traced out by what? By what is the u and v going to move throughout this region? Well, it's going to trace out this surface here. You can think about that. It's traced out by the tip of this vector R of u and v. Okay, so you take u and v, and then you have this vector, and this vector has three components. Okay, this, and this, and then the tip of this is going to trace out this surface here. So imagine that. Think about that. Sometimes at night, you see those laser pointer pointing to the sky, right? Think about this position vector right here. It kind of like those laser pointer pointing to the sky. So it's going to take, it's going to change, right? So it's going to move and move and move like that. And then the tip of that, think about that, trace out this surface, this parametric surface right here. Okay, question here. There's a new concept, okay? So we map this region on the UV plane to a parametric surface. Okay, now let's use some example to understand this a little bit better, okay? So let's identify and sketch the surface with this vector equation. Now, I'll let you work on this for a little while, okay? So think about it. By the way, this is not bread. Looks like bread, right? It's cranberry juice. Okay. All right. I'm gonna ask you guys after you think about it. Okay. So what are the parametric equation for this surface? Parametric equation, x here is equal to what? 2 cosine u, yes. So this is the, oh, okay. This one here is the x, right? Okay. And this is the y, and this is the z coordinate, right? So x is 2 cosine u, y is equal to v, z is 2 sine of u. Okay, so you got it. Good job. Okay. All right. So for any point on the surface, okay. Now take a look at this 3 parametric equation. You see sine and cosine here and here, right? So if you ever see sine and cosine appear in those parametric equation, you think about the identity. What's the identity you think about? Yes, sine squared plus cosine squared equal to 1, right? Okay, so that identity over here, okay, this one. Okay, now in order to use this identity, so we're going to isolate this cosine u and sine u, okay? So we get, or we can do it this way. So we have 2 cosine u squared plus 2 sine u, this quantity square. So that should be equal to 2 squared right here, right? Because of this identity, okay? Now, using this, can you tell me x squared plus z squared, okay? So x and z involve sine and cosine. Can you tell me x squared plus z squared equal to what over here? What should I put in this blank? 4 cosine u plus not 4 sine u. Z is only sine u, right? Okay. Yeah, okay, let's see. Okay. Oh, hey, did I forget a 2? Yeah, 2 sine u. Oh, yes. You got it. Okay. So z squared. Did I forget a 2 over here? X is this. Oh, there's a 2 over here. Oh, I forgot. Okay. So yeah, there's a 2 over here should be. This one here is z, right? This is a 2. Forgot a 2 over here. Okay. All right. So so we have 4 cosine square u plus 4 sine square and u, and that is equal to, what does it equal to? That's equal to 4. Yes, got it. Okay. Now looking at this equation, x squared plus z squared equal to 4. So, and you're going to, what is it? On the xz plane, what kind of curve you get? It's a circle, right? So on the xz plane, it should be a circle, right? This one should be a circle with radius equal to what? Radius equal to 2, right? And center at this origin, right? So that should be a circle like that on the xz plane, okay? Now, what about the whole surface? Okay, so should be circle with radius 2, okay? When you keep the y here constant, okay? So, and then after that, you're going to let the y here vary, right? So you can change, the y here can change, okay? There's no restriction on this v, okay? We don't pay any, we don't restrict this v over here. So y can take on any real number value, okay? So that means that the cross section here will be a circle, right? The curve over here will circle, and for each different y, you're going to get circle. So it's like the circle extended along the y direction. So you get, what kind of surface is this? How do you describe this in word? Is what kind of surface? Is a cylinder, okay? It's a cylinder with radius 2, and the axis is the y-axis, okay? So this curve here will be circle, okay? And as y change, okay? And then you have different, you have circle, they all have the center at the y-axis and radius 2. So it will be a cylinder like this. Question. So that's the surface for this parametric for this three parametric equation, okay, or for this vector equation, okay. So this is called the vector equation for the surface, and these three are called the parametric equation for the surface, okay. They describe the same surface, which is this one, okay. Question? Okay. In this example, remember we didn't put a restriction on the parameter u and v. Okay, so we get this cylinder is going to extend forever. Okay, imagine a really long cylinder, a long pipe, extend forever along this y direction. Okay, however, we can actually restrict the u and v. Okay, for example, if we restrict the u here, go from 0 to power 2, and v go from 0 to 3. Okay, what's u? U was so remember this is the u and this is u, right? U is this angle right there. Right? Think about that. If you go from 0 to power 2, we will get this at the first octane right here. Okay, and then v go from 0 to 3. So along the y direction, y can only go from 0 to 3. Then we get this part of this cylinder, okay, so part of it. So as you can see here, this angle, the u go from 0 to pi over 2, and then v here go from 0 to 3. So this is part of the cylinder, and you want to describe the inward, that will be a quarter cylinder. Okay, it's a quarter of the cylinder with length equal to 3, starting from this xz plane and ended at here, y equal to 3. Okay, so that will be the surface. Question? Now, okay, let's take a look at this picture. This is the region in this UV plane. Okay, that's the D. Okay. Now, and this region under this vector function is going to map to this surface, the blue surface over here. Okay. Now, we are going to, when we try to study this, it's useful to study two family of curve. Okay. What are the two family curve? One family curve is with the u here to be constant. And then the other family will have this v here to be constant. Okay. So the first one will, the first family, we're going to hold the u here to be constant. Okay. And then the other one, we're going to look at the family of curve that has a v here to be constant. Okay, if the u here constant, right, on the UV plane, we're going to get this vertical nice segment here at this region D, right? So you're going to hold the u here to be constant. So you have this plane nice segment over here in this region. And then you have many of those, right? You can pick the u here to be different constant. Let's just pick this arbitrary one. Just pick one over here. Okay. Then it is a vertical nice segment here at the UV plane. Okay. And what happened under this vector function? Now under this vector function over here, the u here is going to be constant. Okay. So equal to u0. So it's going to be, so this one here, the first component, the first parameter is going to be fixed, and fixed to be u0, okay? U0 over here. And then you're going to have this curve, this pink one over here. Okay, I'll make it like it's the one here. This one is going to map to this one. Okay, having the u here to be a constant u0. Okay, this one over in this vector function. Okay, what happened to this vector function? This vector function here, the first component is going to fix. So it only depends on this second parameter, this v over here. So basically, it is a vector function of a single parameter, v, because this one here, the u is fixed, okay? So it only depends on the v. So as v change, it's going to trace out this one, this curve right here, okay? And let's call this curve over here C1. Let's call that C1 over here. C1 only depends, it's going to change as the v here change. U is going to be fixed, okay? This is called a grip curve, okay? Something called this is called grid, grid curve, okay, like this, okay? So this is the grid, this pink one here mapped to this. Similarly, we can fix this v, we let v to be constant, and we're going to have this horizontal line segment over here, right? This horizontal line segment over here. And then under this vector function, what happens? You're going to have, okay, let me write it down. So under that vector function, so this vector function, remember, has u and v, right? But this time we're going to fix this one. So this one here is going to be fixed. Okay. Then what happened under this vector function? Then it only depends on this. So this is this function of this vector function. It depends on this single parameter u. Okay, and it's going to map this into this. Along this, remember the v is fixed, the u is changing. So it's a vector function of a single parameter u. And it is the green one over there. Okay, so, and they are called grip curve. Okay, I have a hard time pronouncing that. Okay, so for example, in our first example, we had those grip curve, right? The first time we fix, well, if we fix the u, okay, so what happens if we fix the u? You fix the u, you're going to get, okay, so if you fix the u over here, okay, u fix, and then let the v vary, okay, you're going to get this horizontal line over here, okay? So you have horizontal line here, or here, or here, okay? Think about along the surface, right? So those horizontal line, okay? When u is fixed. Okay? And what happens when v is fixed? When v is fixed, you're gonna get those circle, the green one over here. I jot it out. So when v is fixed, then you're gonna get those circle. And then when v is fixed over here, you get horizontal line. All right. So those are the grip curve for the surface. How do we get those grip curve? We're going to fix the u, and you get a family of grip curve, and then later on you fix the v, and you get a family of grip curve. Okay, so your grip curve, the pink one and the green one, two family grip curve. Right. So let's talk about grip curve on parametric surfaces. Okay. So when would I use a grip curve? Okay, let's talk about this. The first one. Okay. Someone to read this? Anybody? Oh, Yan? Oh, okay. So Yan with the first one, you read the second. Okay.
Sure.
Okay, Yan, go ahead.
The curve at motion must regularly replace where convention pressure compressor. Such compressors often use spiral tubes that can be modeled using parametric surfaces. Grid curve is one variable described as physics, while grid curve is in another variable described cycles.
Okay, great. Okay, Jason, you can read the second one.
Graphic designers use computers to render many surfaces. Grid curves are used by many computer rendering systems to approximate surfaces using sets of curves defined by pairs of values in the parameter.
Okay, perfect. Okay, the last one. Okay. So, Tracy, would you like to read it?
The model the planet Earth using the parametric surface representation of the scheme. In this representation, the curves in the variables are longitude that connects the North Pole and the South Pole. The curves in the other variable are latitude lines.
Yeah, very good. Now, this is actually a very familiar example, right? Okay. So the group curve here will be the latitude line and also the other one, the longitude. Okay. All right. Now let's look at some example. So group curve is going to help you actually visualize the surface. Okay. So here you can use computer algebra system to graph the surface. Okay. So over here we graph the surface over here. Okay. So we can input this vector function and then we get the surface. Okay. So looks like a spiral up like this, a tube, right? Does it look? What does it remind you? Does it remind you of the tube in the playground, children playground? Okay. Also sometimes can remind you of something like that. Okay. All right. So we're going to see the corresponding group curve. Okay, which group curve have U constant? Which one have V constant? Okay. Oh, you know, cause surface here, right? Oh, yeah. So let me do this. All right. So which one has U constant? Which one has V constant? Okay. So how do we know that? Okay. So we graph this surface, okay, and this is not the whole surface, okay. We shift the U here from 0 to 4 pi, okay. So we have like 2 rotation, okay. Actually, this surface is going to go on forever, up and down, right? Okay, and then we shift that from 0 to 2 pi, okay, like this, okay. This one here has this appearance of a spiral tube, okay, kind of like those tube that you see in the children's playground, okay. How do we identify the group curve? Let's write out the corresponding parametric equation first. So what does x equal to? X equal to what? Huh? That should be not too bad. Yes. This whole thing, right? X, right? Yes. And then this one here will be the y, and this one here will be the z, right? So you got the 3 parametric equations, okay, like that, right? And what happened? Let's think about, let's keep the v here to be constant, okay? So remember, you take turn to keep one of the parameter to be constant. How about we keep the v here to be constant first? And let's think about what happened. If I keep the v here constant, would this part here be a constant? Right? Then that will be a constant, and that's a constant. And this is the same constant. Let's call it constant c. And then cosine of v will also be a constant. I'm going to call that constant d. Okay, constant d right here. Okay. Now, what kind of curve is this? So it's c times cosine u. This one here is g equal u plus this. So what kind of curve is this? This one over here kind of remind you of the helix, right? The helix is this one cosine at t. Okay. And remember here, we have a u like this. Remember the u here varies, kind of like this t over here. Okay. This one, and then this one here is that constant times sine over u. Okay. This one over here, actually resemble this. Okay. The helix. Okay. So there's a connection between this one and this one. Okay. So when you keep the v here constant, then the curve is a helix. Okay. So when you keep this v constant, you have those spiral curve. okay, like the helix. Okay, so you have that one. And what about U constant? So let's investigate on that one. So if I have the U here constant, then this will be constant, this is constant, this is constant, okay? And I notice that this has this, I'm trying to use this identity, sine square plus cosine square equal to 1 on V. And I was trying, okay? So I tried to isolate sine of V and isolate cosine of V. And I put that into this. I had these two equations, okay? And I also noticed that these two are equal. So x over cosine of U is equal to y over sine of U. So y over x is tangent of U, okay? Which means that y is equal to tangent U times x. So it's like the tangent U here is kind of like the slope, okay? Like that, okay? So what will be the grip curve then? The grip curve for this is going to be a circle. It's a circle over here. And for this circle, if you project that to this xy plane, you're going to have this, the equation for this line here, the slope will be equal to, the equation for that is going to be y equal to tangent u times x. Okay, so when you project this line here, project this down on this xy plane, you should get this y equal to mx with m being tangent u. Okay, like that. So so someone say, how can you know that should be a circle? Then we can it says it can be shown that. So it's actually not that simple, right? So we deduce this. So it's going to look like circle. And I actually, in the past, I actually did the animation. What did the animation do here is you're going to see this circle. If you change the U, okay, pick U to be different constant, you get different circle. And you see the circle is going to go along the tube like this. Okay, go down the tube, okay, up and down the tube like this. Okay, so that's the animation do. And further, so if you keep the U constant, look at this. Look at what happened to this. Right? Look at the Z component. If you keep the U here to be U naught, what happened to cosine of V? Cosine of V will change from -1 to 1, right? The minimum will be -1, and the maximum of that will be 1. So Z is going to be between U naught, the one that we fixed, okay, plus 1, and U minus 1. So Z is going to be between that, okay? So you can see here, the Z, when you keep the U here fixed, Z is going to be between U naught minus 1 to U naught plus 1. So that will be the top and bottom of this circle right here. Okay, so that's a grip curve. So when you keep the U constant, you get the circle. Okay, so go back to this one over here. So when you keep the U constant, you get those circle. Okay, and imagine those circle over here go, going to go down the tube. Okay? So like this. For different U, we have different circles and go up and down the tube. And then when you keep this V constant, what happens is it's going to be spiral at the ends. So spiral up like this. Is this one over here? Spiral. And if you draw all those grip curves, and then you can see the grip curve actually help you to visualize the surface a little bit better. All right, so let's look at this example 3. Okay, in example 3, we try to find a vector function that represents this plane over here, passing this point P naught with position function R naught, okay, and contain two non-parallel vector A and B. So here's a picture, Okay, so you can see that. So I have this one. So in this plane, you have this two vector A and B, and they're not parallel. So the interlane of the plane, the blue one, the blue plane here. And we try to find a vector function represent the plane that cuts through this point and have this two. The plane here contains this two non-parallel vectors. Okay? And this one here is the position vector of this point. Okay? So what will be the equation for this plane? All right. So to get the equation, think about if P is any point in the plane. Let's think about this point here, P, on the plane. Okay, we're trying to see find the x, y, and z coordinate of this point P, right? Okay. So we can get from this P naught to P by moving a distance in the direction of A and in the direction of B. Okay, do you guys remember in this homework, I think it's one of the homework problems, it says that suppose A and B are two non-zero vectors that are not parallel, and C is any vector in the plane determined by A and B, then C is going to be a scalar multiple times A plus a scalar times B, okay, for suitable scalar S and T. So which means that, what does it mean? Okay, so that means that this P naught P over here can be represented as a scalar. So let me write down. So the P over this one over here. Now what do we have? We have two vectors on the plane. One is A, the other one is B. Okay, they are non-parallel. Okay, they will determine the plane. And then this is one vector in the plane. Then according to this homework problem that we already proved, okay, then this could be represented by a scalar multiple times this plus a scalar multiple times this. Okay, so any point on any vector on the plane can be represented as a combination of a scalar multiple times this vector A plus a scalar times this vector B. And for that, here they choose the U and B. So U here is, this is a scalar, okay, like that. All right, so over here, we represent this P naught P as U times A plus V times B. Now I'm gonna ask you, what is this, so this R over here, right? We try to find this R, right? This R here is the position vector of this point P. So I'm trying to write a vector equation for this vector for this T over here. So look at this one, R here, and this one, and this one. They form a triangle, right? They form a triangle. Okay. So this R here is OP naught plus P naught P, right? The triangular, right? This is equal to this plus this. Remember in the past we talked about that? If you want to get if you have this, right, you have A, and then you have the vector B, then this one over here will be A plus B, right? So if you point from here to here, this is equal to this plus this. So this one here is equal to this plus this one. What is this? OP naught here is what? R naught, right? And what is P naught P over here? That is being replaced by what? By this one over here, right? Being replaced by this expression over here. So we're going to have that is equal to R naught plus U times A plus V times B. R naught plus this one over here. Okay. Okay. So we got this vector equation for this plane. Okay. Now we're going to write it down. Okay. So there's R of U and V. Okay. So you have two parameters, right? One is the U and the other one is the V. So this one says that if we know this position vector for this point on the plane, okay, and if you know two vectors on the plane, then you can represent the position vector of any point on the plane this way. And you have two parameters, okay? One is the u and the other one is the v. Now, some people will say, well, this is a little bit new. How about we compare this with our past knowledge? Okay, think about this with the vector equation of a line, right? This is vector equation of a plane. Okay, so what is the vector equation of a line that passing this point P naught and with the direction vector here to be A? Do you guys remember? I put it out here. It should be R naught plus A, right? And now what should I put over here then? Well, that will be R naught, okay? And plus the parameter T times the direction vector V, right? Remember A here is equal to this scalar multiple of this V. The V here is the direction vector, okay? So in the past, we talk about this, right? So if we know the point, right? If you know the position vector for a point here, and if you know the direction vector, then you can write out the vector equation for the line this way at that time. Now, let's compare these two together, right? This one here is for the line. That will be R naught, which is the position for this point, plus a parameter, which is a scalar, times the direction vector for that line. Now, when we get to the plane, then we have this R naught here is the position vector for that point on the plane. But this time we have two parameters instead of just one parameter. So you have U and V. And the plane over there determined by two vectors, parallel vector, which is A and B. So you have this. So this is for the line, and this is for the plane. Okay. Good. The next one is a little bit small. Can you see? Okay. So so what are the parametric equation for the plane then? So we write down the vector equation for the plane. So what are the parametric equation for the plane? What does x equal to? Well, let's start with the easy one, the one in the past, right? Do you guys remember the parametric equation for the line? That was the vector equation. So what are the parametric equation for the line? Right? This question of the suppose the direction vector is A, B, C, and then here is x naught, y naught, z naught. That's the point. Anybody remember? Yes, x equal to x naught, right? Plus t times a. Yeah, you got it. Good job. Okay. So is the x coordinate of this? So it's the x coordinate of that point plus t times the x component of the direction vector, right? So what about y? Y equal to what? Y naught plus what? T times t. Yeah, all right. And then z equal to z naught plus c times t, right? Now from here, let's think about this one. That was for the line, right? So what about for the plane? So x equal to what? Okay, from here, let's make a connection between this. So that should be x naught plus what? U times A1 plus B times B1, right? We take the first component of this one, multiply by the scalar here by U, multiply this by scalar here B. Okay, so that is, let me make it larger. Okay, so you would take this this x naught over here, and then plus U times the first component of this vector A, okay, and then plus V times the first component of this vector B. Okay, so that was for x. And similarly, y equal to what, everyone?
Why not do A to the B equal?
Yes, why not? Okay, all right, why not? Because this, okay. And then the last one, z equal to everyone. Yes, you got it. Good job. Okay, all right. So those are the parametric equation for the print. Okay, so you try to compare that with the parametric equation for the 9. Okay, this time we have two components, two parameters, u and v. Okay. Okay, now let's try this example. Okay, example 4. We try to find a parametric representation of the sphere, right? Here is a sphere centered at the origin with radius a, okay? And it has a simple representation in a spherical coordinate. It's just rho equal to a, right? Okay. Do you guys remember in spherical coordinate system, what does x equal to? Looking at the picture over here. X equal to what? X equal to, okay, how do we get this? Okay, let's try this, okay? Right here. So X over here is this, right? But we know from here to here is A, right? Now take this A, and you first want to get this one over here, right? So how do you get this one? This is the right angle. If this is phi, this one here is opposite to phi, so this side here will be A times sine of phi, right? A times sine of phi. So let's put it out over here. So I'm going to highlight this from here to here. That is A times sine of phi, right? Yeah, you got it. Okay. A times sine of phi. Okay. Now we're going to consider this right triangle down here. So x is the adjacent side of this angle theta. So what does x equal to? X equal to this times the cosine of theta. Yeah. So x is equal to a sine phi cosine theta. Okay. And similarly, what does y equal to? A sine phi sine theta. You got it. Okay. And then z equal to what? Z is this right here, right? So we consider this right triangle. This is A, and this is the adjacent side of this side. So it's A times cosine of phi, right? Yeah, good. So it's A times cosine phi. Okay, so we have this. So those are the parametric equation for the sphere. So we have it right here, right? We actually use the two parameter, right? What are the two parameters that we use? What are the u and v? So remember, you have two parameters, right? U and v. In this case, what are the two parameters? The first parameter will be what? Will be theta, right? I'm sorry, not theta. It's phi, right? And the second one is theta. Okay. So this is the u. This is kind of like the v, and this one over here is the u. So we have the two parameter here, u and v. So phi and theta. Okay. So these are the parametric equation for the sphere. What is the corresponding vector equation for the sphere then? If you get the parametric equations, you should be able to get the vector equation, right? You can just put them in each component. Okay. So then we have the vector equation for the sphere. For the sphere over here, do you guys remember for spherical coordinate? Remember phi over here is going to be between 0 to pi, right? So phi equal to 0 here, and then all the way to pi is going to be here. And then theta is going to be between 0 and 2 pi. So one rotation, 0 to 2 pi. So the parameter domain is this rectangle. Okay. So phi go from 0 to pi, and then theta go from 0 to 2 pi. Is this rectangle over here. So what are the grip curve? Let's think about the grip curve. If you keep phi constant, okay, what happens if you keep phi constant? So let's keep the phi here to be constant C. So that will be constant, right? So the G coordinate will be constant. And then, this two over here, you can use so when you square this plus the square of this, you should get equation of what kind of curve? Equation of a circle. Yes, you got it. So then, if you keep the phi constant, you're going to get a circle. You see that the D here is going to be, when phi is constant, cosine phi is a constant, so this is a constant, right? So the G coordinate will be constant over here. And square this plus square this, you get x squared plus y squared will be equal to, in this case, it should be a squared, okay? So you're going to get a circle, this pink circle over here. So this is going to map to here. So that is the group curve, okay? And when you let phi to be different constant, and you have different circle over here, okay? So remember, we think about this as the Earth, right? This is called what do you call that? It's the latitude or longitude? Latitude, right? It's kind of the latitude of it, right? Okay, the circle of constant latitude, okay, including the equator, okay, constant latitude. What about if you keep the data constant? The data constant will be this horizontal line segment here. When data constant, which one is constant? So sin data, cosine data will be constant, right? Okay. And you will have this square plus this square over here. Okay, you do the math right here. Then when you do the math right here, you should get this. It's going to be the how do you say this word? Meridian. Is it meridian? How do you say this word? Anyone? Huh? Meridian? Meridian? Okay, meridian. A semicircle, okay? Semicircles. The green one I highlighted over here, okay? The one I highlighted over here is the meridian. This is semicircle over here, okay? That connects the north pole and the south pole right here. So you have group curve will be circle like this. And, those are the latitude, and then this one here kind of like the longitude. I want someone to read this note right here. How about who want to read this? Kenny, you read this note from here to here. Yeah, Kenny Chen. Kenny, so Kenny Baker.
That the curve for a sphere are curves with constant latitude or constant longitude. For each general parametric surface, we are really making a map and the grid curve is similar to lines of latitude and longitude. Describing a point on a parametric surface, like the one in figure 5, by giving specific values of u and v is like giving the latitude and longitude of the point.
Okay, perfect. Good job. Okay. All right. Okay, I want someone to also read this one here. Some marker here. How about Renee? Read from here to here.
Uses of parametric sphere graphics. Figure 8 shows the result of trying to ground the sphere. X squared plus y squared plus z squared equals 1. By solving the equation for z and graphing the top and bottom hemispheres separately. Part of the sphere appears to be missing because of the rectangular grid system used by the computer. A much better picture in figure 9 is produced by the computer using the parametric equation solved in figure before.
Okay, very good. So if you use the rectangular coordinate, then it happened to be like this, right? It's part of missing, right? But then if you use this is better, okay?